Good day, everyone. This is Shelly Dabun, and I am going to discuss regarding the problem 7.33 on the book of Mechanics of Materials by Beer and Johnson. In problem 7.33, we are asked to solve problem 7.9 using the Morse circle. So before we go ahead and jump into our calculation, let's first know what is Morse circle. Morse circle is often used to calculations relating the mechanical engineering for the material strength. It can be used to find our principal planes and principal stresses by converting them into a graphical representation, and luckily it is one of the easiest ways to do so. So now that we know what Morse circle is, let's go ahead and jump into our problem 7.33.
We are going to solve 7.9 using the Morse circle. We're given the state of stress right here, and we are asked to determine the orientation of planes of maximum in-plane shearing stress, the maximum in-plane shearing stress, and the corresponding normal stress. So what we're going to do is we are going to convert these values into kilopound force per square inch, and this is the result. So let's go ahead and jump into our problem. So here I've kind of summarized the process that I use in drawing Morse circle. The first thing that we do is we establish a local coordinate system in the stress element. I'm gonna go ahead and use X as my horizontal and Y as my vertical. So the next thing that we're going to do is we're going to define stresses. Our sigma X, because it's causing tension in the face, is equal to 9 psi. Now notice that our sigma Y is causing compression in the face of the stress element, and so the sigma Y to negative 6 psi. Now for our shear stress right here, it's on the positive X phase and the positive Y direction, so this is going to be plus 4 psi. Now that we have our stress defined, we're ready to draw our coordinate axis. After we do that, we are now going to define our center. So the center is sigma average 0, and to find our sigma average, it is equals to the sigma X plus sigma Y over 2, and we have a value of 1.5 psi, and now we know that our center is at the coordinates of 1.50, and the first point on the outer radius, which we're gonna call as X, is the sigma X and the negative tau xy, and Y is going to be the sigma Y and the positive shear stress. The next thing that we're gonna do is calculate the radius, and the radius is just by Pythagorean theorem. It is this distance and this distance. So since X was 9 and negative 4, which should make this distance right here, let's call this point F, making that distance right here 7.5. And this would be 4. So the radius is then going to be 7.5 squared plus 4 squared, which is equals to 8.5 psi. So in our problem, the first thing that we're going to determine is the orientation of the planes of maximum in-plane shearing stress. And to do that, we need to find this angle right here that we're going to call alpha. That is equal to 28.0576 degrees. First, we're going to define our theta A. That is just half of our alpha, 14.0288 degrees. We're going to find our angle of D and our angle of E. To be able to do that, we're just going to take the value of our theta A and plus 45 degrees. That is going to equal to 59.0288 degrees. And for this one, we're going to subtract it with our 45 degrees, giving us a theta value of negative 30.9712 degrees. And this now is our orientation of the planes of maximum in-plane shearing stress. For the letter B, we are asked to determine the maximum in-plane shearing stress. And we know that the maximum in-plane shearing stress is just actually equal to our radius. So that is our answer. The corresponding normal stress is just actually equals to the sigma average. Is equals to 1.5 psi. So notice that the first value that we are given are in the form of megapascals. Therefore, our value for the maximum shearing stress is then going to be equals to 59.5 megapascals. And for our normal stress, it's going to be equal to 10.5 megapascal.
And now we are able to solve our problem 7.33 by solving our problem 9 using the Mohr circle. This is the end of the video. Thanks for watching.